Okay, so we're going to take a look now and focus in on one type of organic compound or hydrocarbon that we introduced in the previous section, which were called the alkanes. Right, remember the alkanes are an example of a saturated hydrocarbon, and I'm going to abbreviate hydrocarbon as HC from this point onwards. And remember that means that there's just carbon to carbon single bonds. So only carbon-carbon single bonds present. So we're first going to take a look at how we name these alkanes. And it's the same sort of naming system that we are going to be using throughout this entire section, or throughout the remainder of the course, actually. So we're going to be using a system called the IUPAC, which is just a systematic way, which, by the way, is the same system we've been using to name all the other compounds, the other ionic and covalent compounds we've seen before. They also have rules that govern organic compounds, and we're going to use those rules here. So a systematic way to name our compounds. And really what it boils down to is when you have your alkanes, or actually any other type of organic compound, the first thing you need to do is to establish the longest continuous carbon chain. Okay, and that's extremely important. That's going to be the basis for naming our alkanes and some of the other compounds as well. And then we're going to use prefixes to denote how many carbons are in the longest chain, and then the name for the alkanes will all end in ANE. Right, so that's a clue right away that you're dealing with an alkane, the fact that it ends in that ANE. So let's talk a little bit about some of the prefixes that we're going to see. So the prefix for 1 is meth. The prefix for 2 is eth. The prefix for 3 is prop. The prefix for 4 is bute. The prefix for 5 is pent. For 6, it's hex. The prefix for 7 is hept. For 8, it's oct. For 9, it's non. And for 10, it's dec, right? And you've probably seen, actually we did see some of these prefixes before when we looked at our covalent compounds, but there's some new ones here that we are encountering, right? So for instance, the meth, eth, prop, and bute, right? We haven't seen those before, but from 5 through 10, we've actually used those in our covalent nomenclature. So those are prefixes that are going to tell us how many carbons are in the longest chain, and the ending for your alkane is going to be ANE. So for instance, if I have a 1 carbon alkane, well, the prefix for 1 is meth, and then because it's an alkane, it's going to have that ANE ending, right? And it's that simple. If I have a structure and there's a total of, the longest chain is 7 carbons, so we know the prefix there will be hept, and if they only see carbon-carbon single bonds, it would be an alkane. Right, so this means it's a 7 carbon alkane. Right, so you need to know these prefixes 1 through 10 when it comes to the nomenclature of the organic compounds. And here are some examples of the first 10 alkanes that we have. So we have methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane, right? They all have that ANE ending, which tells you that they are all alkanes, right? What you'll also notice is that the formula for your alkane actually conforms to a general formula, and that's CnH2n plus 2, right? So for instance, for a 7-carbon alkane, we can actually predict the chemical formula. So C7 and then H 2 times 7 plus 2. All right, that would be C7. 7 times 2 is 14, plus 2 is 16. And that would be the formula for heptane. And if we go back to our table, right, we can see heptane right here. C7, H16. Right, so that's a shortcut for determining the formulas. All right, so let's take a look at how we represent these structures. We sort of used them a little bit before, but I want to take a closer look at them now. All right, so let's focus in on maybe a 4-carbon alkane. So 4 carbons, we have 1, 2, 3, 4. Those are 4 carbons bonded, single bonded to each other. The remaining bonds to carbon, remember carbon likes to form 4 bonds. So this carbon here on the left needs 3 more bonds. The one in the middle needs 2. That one needs 2, and the one on the right needs 3 more to have a total of 4. And those bonds are going to be to what? Well, if it's a hydrocarbon, those bonds are going to be to hydrogens, right? So we just fill in the H's. Like so. And when we show all of the atoms and all of the bonds involved, this is our expanded. I'm going to write this up here to the right side. This is your expanded structural formula. Right, we can then take that expanded structural formula and condense it like we did previously. Right, so we have a C and 3 H's. So a C and 3 H's. That's connected to a C and 2 H's. That's connected to another C and 2 H's. That's connected to a C and 3 H's on the right side. Right, so this here would be your condensed structural formula. Right, just a quicker way to represent the structure for an organic compound. Okay, and then a much more efficient way to represent the chemical formulas and the structures for organic compounds is by using what are known as skeletal or line angle formulas or structures. And we're going to use butane as our example again. All right, so butane has the formula C4H10. There's our expanded structural formula that looks like this. We saw that we can convert that to a condensed structural formula that looks like this. And the way that the line angle formula works, and it takes a little while to get used to it, but it's really, really, really quick to draw the structures for organic compounds. So we're going to, as the name suggests, we're going to use lines and angles to draw the structures. So we're going to start with a line, and you can draw it either going up or down. So I'm going to draw my first line going up. When you have that line, there are a couple things to note, right? Where this line starts, right here, there's a carbon. Where the line ends, so there's a carbon here at the start of the line, there's a carbon at the end of the line. If I were to continue my line now, there's a carbon at the end of the line again. Right, and what you'll see is that where those two lines intersect, right here, there's a carbon there as well. So right now, in this, it looks like an A that I just drew, this actually has 3 carbons in it. 1, 2, 3. And if I were to extend my line one more time, right, then there's going to be a carbon at the end of that line as well, and that'll be my carbon number 4. Right, this structure that I just drew, this is the exact same thing as the condensed structural formula, and it's the exact same thing as the expanded structural formula, right? And this here is called a line angle or skeletal structure. So a couple of things to note. There is a carbon at the start and end of a line, and there is also a carbon where 2 lines meet. All right, so I'm going to erase some of this stuff here. All right, so there's a carbon at the start and the end of a line. So there's a carbon right here, and there's a carbon at the end of the line, and there's a carbon where lines meet. So there's a carbon right here, and there's also one right there. Right, so those are our 4 carbons. Now you'll notice that hydrogens are not shown. And that's because they are assumed to be there. And how many are assumed? Well, as many H's as needed to give carbon 4 total bonds. All right, so if we go back now to really what we're saying is that if I were to make a comparison, if this is carbon 1, 2, 3, and 4 in my condensed structure, well, that corresponds to carbon 1, 2, 3, and 4 in my line angle structure. So carbon 1 over here, there's your C. Even though you don't see those 3 H's, they are there because that carbon has to have those 3 bonds to hydrogen, so it has a total of 4 bonds. For this carbon number 2, there it is. Right now it's shown in the line angle structure. There's a bond to a carbon on the left side. There's a bond to the carbon on the right, so it needs 2 more bonds to H's. Same thing with carbon number 3 right here. In the line angle structure, you can see those 2 bonds to carbons on either side. It needs 2 more bonds to H's to complete, or to make sure it's got 4. And then our last carbon here on the end is going to need 3 H's on it to complete, or to make sure that it has 4 bonds. Right, so the line angle structures are really, really quick ways to draw the structures for your organic compounds. All right, so let's just take a look at another example. If I wanted to draw a 5-carbon alkane, All right, and I'm going to say line angle. I'm going to start with a line, right? And that first line already accounts for 1, 2 carbons, and I can extend it 3, 4, 5. And that's it. That's a 5-carbon alkane. We can actually name that now. So 5 carbons would be pent. Alkane would have that A-N-E ending, and that would be pentane. Right, similarly, I can extend that even further. A 10-carbon alkane. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that would be decane. Right? You're able to draw the structures really, really quickly, as opposed to drawing out the expanded structural formula where you're showing each bond and each atom. The line angle structure makes it a lot easier to represent the organic structures. All right, so here we have some examples of how butane can be represented. So we looked at butane before. There's the expanded structural formula. And then we have several ways here to represent the condensed structural formula. And you notice that they kind of all look slightly different, but these are all the same. Right? And the reason why they're the same is because when you have your carbon-carbon with single bonds between them, that actually means that they can rotate. Right, so you can draw it as a straight line, or you can draw it with a bend in it. You can draw it sort of zigzag. You can draw it as zigzag that way. You can draw it with a kink in the tail. You can draw it like that. You can draw it from top to bottom. They all represent the same thing, because when you look at the longest continuous carbon chain in all of these, it's 4, right? So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, etc. Right? So if you look at every single one of those, the longest chain, the longest continuous chain, carbon chain, regardless of bends in that chain, right? So it can be a straight chain like this, or it can have a bend in it, right? The longest chain is still going to be 4 in every single one of these. So if you see that, don't get confused, right? Because that carbon-carbon single bond can actually rotate around, and it can produce these little kinks or these or produce a carbon chain that's not straight. Okay, so let's take a look at another example. So it says, given the expanded structural formula, provide the molecular, the condensed, and the name. All right, so the molecular formula, we're just going to take a look at the different number and types of atoms that we have. So we have 1, 2, 3, 4, 5 carbons, and we have a total of 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 H's. Right? That's the molecular formula. That's the type of formula we've been dealing with throughout the entire course so far. The condensed structural formula, all right, all we're doing now is combining or condensing it. So we're going to start off with a CH3 that's connected to a CH2. That's connected to another CH2. That's connected to another CH2. And then it ends with a CH3. Right, so you'll see, and we've seen this actually a couple times already, the beginning and the end of the carbon chain are all CH3s at the end, and then in the middle we have these CH2s, which function sort of like bridges in the middle. And then the name for this then, with a 5-carbon alkane, so it's 5 carbons, and it's an alkane because they're all carbon-carbon single bonds. 5 carbon would be pent. An alkane would be ane, so that would be pentane. If we wanted to draw the line angle structure for this, it would be 1, 2, 3, 4, 5. All right, and that would be pentane. Okay, so I'll leave the learning check 2 for you guys to practice. I want to jump into another aspect of organic compounds that we talked about at the beginning, which was the fact that your carbon-containing compounds can easily form cycles or rings. And when you have your cycle or rings that contain carbon-carbon single bonds, we call them cycloalkanes. So these are ring structures or cyclic structures. And again, now because they're alkanes, they're going to contain carbon-carbon single bonds. Right? Because now we're essentially closing a chain to make a ring structure. This is going to have 2 fewer hydrogen atoms than the open chain form that we saw previously. All right, so for example, if we had something like propane, which we now know is going to have 3 carbons and a total of 8 H's, right, what we can do is we can actually take those 2 ends and bring them together and close that that chain to make a ring, right? So propane, the line angle structure is just like an A or an upside down V. The cyclopropane would just be a triangle, right? We just close the loop to make a ring structure. If we were to draw the expanded structural formula for cyclopropane, it'll look like this. Right, so we lost 2 of those H's because we made a new bond between 2 of those carbons. Right, so propane would be the straight chain form, and now we have a ring structure. So when there's a ring structure, we include the prefix cyclo in front of it. So cyclo meaning ring, and then prop meaning 3 carbons, and then ane meaning that it's an alkane. Right, and cyclopropane would be the simplest or the smallest cycloalkane that you will ever see. Right, so here are some other ones that we, as we start, making the molecules bigger and bigger. So a 4-carbon ring structure would be, so let's just name these. All right, so we have here a 3-carbon ring. So first of all, ring structure would mean that it's cyclo, 3 carbons, prop, carbon-carbon single bonds, ane. The one right next to it, again, a cyclic structure. So cyclo. Now we have 1, 2, 3, 4, right? 1, 2, 3, 4 carbons in the ring. So that's bute. And then all single bonds would be ane. Continue that. So again, we have a ring structure here. This would be cyclo. We have 1, 2, 3, 4, 5. So that's pent. All single bonds, cyclopentane. And here again, we have a ring structure with 1, 2, 3, 4, 5, 6. So that would be cyclohex. All single bonds, cyclohexane. So in these cases, you don't have the longest carbon chain, but you do have a ring structure, right? And what tells you how many carbons are in the ring would be that middle part of it. Right, which is the prefix that we use for the longest carbon chain. In this case, the prefix for the number of carbons tell us how many carbons are in that ring structure. All right, so if we wanted to name these structures, right, this is a really good example of going in the other direction. Now you're given the structure and you have to name it. All right, so let's take a look at the first one. Remember, you're going to start counting the carbons. If you have a chain, you start at one end of the molecule and you work your way all the way to the other end. So there's a carbon here. That's 1. There's a carbon there. That's 2, 3, 4, 5, 6, 7, 8. Right, so 8 carbons is the longest chain. The prefix for 8 is oct. These they only have carbon-carbon single bonds. So that would make it an octane or an alkane. And that's it. For the second one, or for B, we don't have a straight chain. Instead, now we have a ring structure. Right, so we're going to use the prefix cyclo, which tells us it's a cycle or a ring. And let's see how many carbons are in that ring. We have 1, 2, 3, 4, 5. So the prefix for 5 would be pent. So cyclopent. They're all carbon-carbon single bonds. So cyclopentane would be the IUPAC name for that structure. All right, and you can take a look and you can name these ones here in Learning Check 4 to get a little bit more practice.